Morning, guys. Welcome to a day of virtual notes. I know that because we have in the afternoon, we have our assessment. I didn't want those people in the afternoon to fall behind, and I do want to kind of keep us moving. So we have a day of virtual notes to help finish up our notes on sequences. I did include a PDF of the notes on the Canvas module in case you didn't get it the other day. So let's jump in like we normally do. We have a warm-up to start here. So if you want, you can pause the video so you get a chance to try it yourself. Otherwise, I will jump into an explanation right away. So let's say I'll jump in an explanation in 5, 4, 3, 2, 1, 0. All right, so it says let g be a continuously differentiable function with g of 1 equal to 6 and g prime of 1 equal to 3, and it asks for the limit of this rational expression. So as always, the first thing we would do is plug in what we know about the limit. We would maybe try to plug in that x is approaching 1. And if we do that, we'll see that the integral on the top would be the integral from 1 to 1, which we know that any integral that starts and stops in the same place actually collects no area, so the numerator would be 0. And in the denominator, if we plug in 1, we get g of 1 minus 6, but they tell us that g of 1 is equal to 6, so 6 minus 6 would be 0. So at that point, if I saw something like 0 over 0 or infinity over infinity, I know that that's indeterminate form, so I know that I could use L'Hopital's. So L'Hopital says you're allowed to take the derivative of the numerator and the denominator separately and then try reevaluating your integral. So if I try to take the derivative of this expression on top, I notice that I'm taking a derivative of an integral. And I know since those two things cancel each other, this actually ends up being part of FTC part 2. So we can sneak back in our limit. We have the limit as x approaches 1. If we take the derivative of this expression in the numerator, remember we're allowed to take the upper bound. We're allowed to plug it in and then multiply by the derivative of the upper bound. So if I take x and plug it in for t, I literally get g of x like this, right? And then if I multiply by the derivative of the upper bound, that's just 1, so that's not going to change g of x at all. And then if I take a derivative in the denominator, the derivative of g would be g prime, and then the derivative of negative 6 would go to 0. So I'd be left with an expression like this. So now you'd be thinking, well, how am I supposed to know what g of 1 is and g prime of 1? But that's the reason why they gave you these two facts right here. So then if you reevaluate your limit using L'Hopital's, you can plug in 1. You'd get g of 1 on the top, which is 6. You would get g prime of 1 on the denominator, which is 3. And of course, 6 divided by 3 is 2. So at that point, you would have your answer. The final answer in this case is D. It's just an interesting case of L'Hopital's. And notice they can sneak in the fundamental theorem of calculus part 2, and they can get a little bit more knowledge as to what you know all at the same time. So they're really big fans of these kind of questions on the AP test where they can test more than one topic at one time, and it's really not that bad. So just watch out for things like this. Normally if they give you a fact, then at some point in your work you're going to use it. So just look out for those things where they give you a point that goes together in the original function or in the derivative. All right, so there's a warm-up. We do have our assessment this afternoon, but most of you know that. So please have your take-home portion ready to rock and roll, so that way we can just add on to it for the live portion. We started talking about sequences on Monday. We're going to continue that conversation today and hopefully finish it so that next week we can start series. So we said a sequence is just a list of numbers, right? And we know that we have these subscripts. These subscripts will tell us what term of the sequence that we're in. And we know that sequences are generally written as a lowercase letter followed by the subscript n, where n can change. It's just the nice positive integers or the counting numbers. We did say that we can do a couple things with them. We want to determine the convergence and divergence of sequences. We know if they converge, they get closer to a number. And if they diverge, they get closer to negative infinity or positive infinity. They go outwards where they're not actually getting closer to a quantifiable number. They're getting closer to something that's not quantifiable. So these kind of words are still part of the conversation. We did say that we can take limits of sequences because as mathematicians, we don't want to sit and write 1,000 terms of a sequence to find out what's happening with it. We'd like to take its limit. So we know that the limit is really going to end up being the horizontal asymptote. So those little rules that we know about the elephant rules will be things that kind of come back into play. In terms of a limit of a sequence, we can treat the sequence like a function. And if we treat the sequence, so notice here the notation, if we treat the sequence like a function, then we can take the limit of that sequence as we normally would for a function, and whatever comes back for the limit will actually be the limit of the sequence. So we did a couple examples on Monday. We do have the properties for the limits of sequences, but they exactly mirror what we know about functions. That's the clever trick of treating the sequences like functions. And then the last thing that we talked about on Monday was the idea of a factorial, right? We did say that n factorial would be like saying take some number n and multiply by all the nice numbers before it. We did also mention that there were differences in notation, right? So this would be something on the side here. This would be like 2 times n factorial. Where if we go to the bottom, that'd be like saying multiply n by 2 first and then apply its factorial. So if n was 10, the example that we did on Monday was like 2 times 10 factorial. And if n was 10, then 2 times 10 would be 20. This would be 20 factorial. Notice that makes a big difference. 20 factorial is going to be very large in comparison to 2 times 10 factorial. We also know that 0 factorial is 1, and we did show that as to why it's equal to 1. There was like a quick proof for it. So this is kind of where we left off, and that's where we'll jump back in. So then on the notes, you won't see this little section on factorials, but I think that they're good examples to write down, especially in a couple sections. We're going to be expected to do more things with factorials. So if you have a strong understanding of what they are and how to use them, then I think those sections that we have to do will be a lot easier when the time comes. So how about something like 6 factorial? We did say that was like 6 times 5 times 4 times 3 times 2 times 1, right? And there is a calculator button for it. So if you go into your calculator, if you hit math and then go over to PROB, probability, on number 4, you'll see that there is an exclamation point. That's going to be your factorial. We did say that 0 factorial was equal to 1. And the last one that's kind of important for where we're headed is how about something like n factorial, right? So then if it messes with you just as n, then think about n as a number, right? What if it was 6 factorial, then 6 times 5 times 4 times 3 times 2 times 1? But this is saying, let n be the number that you're starting with. So then if I start with n, then the number before it would be n minus 1. The number before that would be n minus 2, and so on, right? It's going to be all the nice numbers, then the integers before n, and then you would say you're going to multiply all the way down. And you could say dot, 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 because you don't know how far it is. N could be something really big, like 1,000. Then it would come down to like 4 times 3 times 2 times 1 here at the end. So this would be kind of helpful to know that n factorial is just saying take n and multiply it by all the nice numbers before it. All right, so then how about simplifying factorials? So something like 10 factorial over 5 factorial. So we know that 10 factorial is the same thing as 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 and so on, right? But if we get all the way down to 6 and we notice that we're dividing by 5 factorial, then we can say that 10 factorial is these 5 numbers being multiplied times 5 factorial, right? Isn't 5 factorial 5 times 4 times 3 times 2 times 1? So then on the bottom, if you have 5 factorial, they would actually cancel each other out, and you would be left with something like 10 times 9 times 8 times 7 times 6. And you definitely can find out what that number is, but for my purposes, this is how you would simplify a factorial. So letter B would be very, very similar, so I'll skip that one. The idea is basically the same. How about something in C though? So notice that if we were doing letter C, that you have 9 factorial, right? So this is 9 times 8 times 7 times 6 and so on. So then if you wanted to, you could stop there because I see a 6 factorial here in the denominator. So I can say 9 factorial is 9 times 8 times 7 times 6 factorial all over. Now I'll write out 3 factorial. This is 3 times 2 and usually times 1, but you don't need to write it. We know times 1 is not going to change anything. And then technically times 6 factorial. So then these two 6 factorials could cancel each other out. And the neat part here is you could actually do a little bit of reducing if you want. So you notice that you have 9 over 3, which is 3. You have 8 over 2, which is 4. And then you have 7. So then if you wanted to, you could go into the calculator. You could find out what this multiplies to, and that would be your final answer. So it's kind of nice. If you have factorials, maybe start with the bigger one so that you can cancel that piece. And then you can reduce because at the end of the day, you're talking about reducing expressions that have multiplication in the numerator and the denominator. So if you want, you can crunch the number. So how about something like letter D? Maybe you pause the video for a second and try it for yourself. How would letter D reduce? So letter D, you could start with 12 factorial. You notice the bigger factorial on the bottom is 8 factorial. So maybe you say this is 12 times 11 times 10 times 9 times 8 factorial. Okay. So maybe I'll put 8 factorial on the right side. And then for 4 factorial, I know that's 4 times 3 times 2. So then the 8 factorials will cancel each other off. And then if you want, you can start reducing things. Maybe the first thing you would reduce is 12 over 4. So I know this is 3. I maybe see 10 over 2 next. So I know that that's 5. If you want, you can sneak the 11 in between. So then that would be 5 like this. And then last but not least, you see even 9 and a 3. So maybe you would say this is 3. Then you could go into the calculator. You can multiply that part out. And then you would have your reduced version of this expression. So factorial is really not that bad to work with. You can get away with the fact that you know that factorial is just a number times all the nice numbers before it. And that will help you do some canceling, very similar to what you're familiar with and what we've done before a lot in Algebra 2. All right, so let's keep rolling. So let's say we get to this one. Now this one says, can you simplify these factorials? Can you write them in another way? So what if I give you something like 12 times 11 times 10 times 9 factorial? Well, notice that 9 factorial is 9 times 8 times 7 times 6 times 5, right? And then we're timesing it by 10, and then we're timesing it by 11, and then we're timesing it by 12. Won't that be all the nice numbers from 12 all the way down to 1? So really, if we have 9 factorial multiplied by 10, that would be 10 factorial, times 11, 11 factorial, times 12, 12 factorial. So in this case, if you're simplifying it, you could say that would be the same thing. Now from here, it starts to look a little bit different, but it's the same idea, right? So I have 72 times 7 factorial. But then you might think to yourself, well, it went from 72 to 7, so that can't be written as a factorial. But think about things like 72. Isn't 72 9 times 8? So this would be saying 9 times 8 times 7 factorial. Well, that's all the nice numbers, right, from 9 all the way down to 1. So this would be the same thing as 9 factorial. How about in letter C? This is saying n times n minus 1 factorial. So n minus 1 factorial is saying everything less than n. So like one thing less than n, and then all the nice numbers before it. So for example, maybe you do it with like a small number, right? What if you said that that n was 4? That might help you think of how this works. Then you would have 4 times, well, n minus 1 would be 3 factorial. That would be 4 times 3 times 2 times 1. So wouldn't another way to say that would just be 4 factorial? So if you apply it in a generic sense, if you're saying n minus 1 quantity factorial is saying n minus 1 times all the nice numbers before it, but then you times it by n, this would actually be the same thing as n factorial. So it kind of makes sense. All the nice numbers before n minus 1 times n minus 1 times n factorial. All right, so if you want to pause the video, you can try these ones real quick. Otherwise, I'll jump straight into explaining it. So feel free to try if you want. So now notice letter D, we're given n factorial, which is n times all the nice numbers before it, but then we're timesing by the number after n plus 1. So in this case, again, you could do n equals 4 if you want. You would have 4 factorial times 4 plus 1, which is 5, but then that would be 5 times all the nice numbers before it, so that would be 5 factorial. So if you apply it in a generic sense, if you say n factorial, that's n times all the nice numbers before it, then if you multiply it by n plus 1, then this would just simply be n plus 1 and a factorial. E is a little bit more interesting because you see the n minus 1, but then you see n squared plus n. But chances are your brain is probably telling you to do something with that, and maybe it's telling you to factor it. So if you factor it, you could say n is a GCF. The leftovers would be n plus 1. So then if you rewrite this, you have n minus 1, and then that would be factorial, times n plus 1. So now notice you have n minus 1, which is 1 less than n and all the nice numbers before it being multiplied, times n. So together these two things would be n factorial. But then we're multiplying it by the number after n, the next nice number. So this would be n plus 1, and it would be factorial. How about this one next to it? So we have n plus 4 times n plus 5 times n plus 3 factorial. I would start with n plus 3 factorial, right? That's 3 bigger than n, and then multiplied by all the nice numbers before it. But then we're multiplying it by n plus 4 and n plus 5. So notice that n plus 4 is just one more than n plus 3. So if you multiply these guys together, wouldn't that have to be n plus 4 factorial? But then you're multiplying by an n plus 5, which is the next nice number after n plus 4. So then this would just end up being n plus 5 and then a factorial. All right, so not bad. Once you get the rhythm down, it makes sense as to where things are going and why they're written the way they are. So now things start to get even more interesting. How about these factorials? So if you want, again, you could pause the video. Otherwise, let's jump in. Let's see what happens. So here we have n factorial. We know that we can factor this expression. That's what most people would want to do. So two numbers that multiply to 2 and add up to 3 would be 1 and 2. So this would be like saying multiply by n plus 1 and multiply by n plus 2 if we factored it. But then notice that that's n factorial, so n times all the nice numbers before it, times n plus 1, times n plus 2. So all together, if you go down the line, you'd have n plus 2 times all the nice numbers before it, which is n plus 2 quantity factorial. How about something like in h, right? So I'd say for these, h and I, just rewriting it I think is kind of helpful. So let's say we had n factorial. We know that n factorial is n times n minus 1 times n minus 2, and then dot 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 all the way down to like 2 times 1. And then how about on the bottom? Well, we know that that starts like n minus 2, and then you multiply by n minus 3, right? And then all the way down to 2 times 1. But then what do these things have in common? Wouldn't they have the n minus 2 in common and then everything before it? So then if you go down the line, you would see all this extra stuff would cancel, which would leave you with n times n minus 1, which you could distribute. But again, the whole idea here is just knowing how does it cancel. So it's kind of a neat trick. And I would say this is exactly the thing that we would need to know for the next couple sections to make our lives a little bit easier. So how about I? So notice I starts with an n plus 2 factorial. So then if you're kind of working your way through it in a similar fashion, then you could say that that's n plus 2 times n plus 1 times n factorial. So maybe I'll kind of split it here so that we don't get confused. So we can say this is n plus 2 times the one before it, which is n plus 1, times n, and then times n minus 1 and everything before it. So if you wanted to, we could call that n minus 1 factorial. So then if the bottom is just n minus 1 factorial, those guys would cancel off, and you'd be left with something like, maybe write in order n plus 1, and n plus 2. So notice it's the same thing that we did with the numbers, just now they're making it generic and leaving it in terms of n. If it gets confusing, let's say you start, your head starts spinning, then just imagine you're plugging in a number in for n, and then think about what happens if you plug in that number. My default is always putting something small like 4 or 5. And then if you know what's happening with that number, then you might be able to say what's happening in a generic sense to that variable n. So if it helps, think about a number like n equals 5 or n equals 4, and I think that makes it better. All right, so if you wanted to try a couple, you could try these. Otherwise, I'll just jump into explanation, and then I think I got a couple more, and then we dive into the rest of the conversation. So, all right, let's see if we can do it. So if you could take a second, try it on your own. What do you think about these factorials? So just like we did the last ones, you could say n factorial is the same thing as n times n minus 1 times n minus 2, and then so on, all the way down to maybe like 3 times 2 times 1. How about on the bottom? We have n minus 1 factorial, so that's n minus 1 times n minus 2, all the way down, dot, 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 times 3 times 2 times 1. So in this case, notice everything will cancel. So really, this is just a fancy way of saying the only thing left over would just be n. You could do the same thing for letter B. You could say n plus 1 factorial starts with n plus 1, but then it multiplies by n and everything before it. So then if you have the n factorials, they would cancel, and this would leave you with an n plus 1. If you do letter C, you can say start with n plus 5, but then you multiply it with the one before it, which is n plus 4, and then all the ones before that would be n plus 3, and then factorial for all the ones that are smaller. So if you divide by n plus 3 factorial, the n plus 3 factorials cancel and leave you with n plus 4 times n plus 5. At that point, the order would not matter. I usually put them in order from smallest to largest, like n plus 4 times n plus 5. But we know since we're multiplying, the order of multiplication doesn't matter. How about these last three? So these last three here. So then if you have n minus 2 factorial, right, and on top you could say this is n minus 2 times n minus 3, and then maybe dot, 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 times 3 times 2 times 1. How about on the bottom? Well, that would say start with n minus 1, then multiply by the ones before it, like n minus 2, dot, 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 all the way down to 3 times 2 times 1. So that means I think everything before or everything after n minus 1. So in this case, you would have all these things that are going to cancel off. You have an n minus 1 in the denominator, but you would have a placeholder of 1 up into the numerator. So this would be 1 over, and then n minus 1. How about letter E? You would have n plus 3 times n plus 2 factorial, which is n plus 2 times all the things before it, which is n plus 1 factorial. So then if you divide by the quantity of n plus 1 factorial, then those guys would cancel off. Then you'd be left with n plus 2 times n plus 3, or flip-flopped n plus 3 times n plus 2, tomato, tomato. How about in letter F? If you start with n minus 4, then you'd multiply by the thing before it, which is n minus 5, and then all of those things before that. So that would be your factorial all over n minus 5, and this is a factorial. So the final answer for this guy would be something like n minus 4. So in a nutshell, there's a quick and easy conversation about simplifying factorials or rewriting them that I think will be helpful. So hopefully it made sense. If not, ask me a question. Ask me to stick around after the assessment today, or send me an email, and I'd be happy to explain it a little bit further. Otherwise, we're kind of on to the next one. So could we order these functions from by rate of growth from least to greatest? So what would be the slowest growing function? What would be the next fastest growing function? On your paper, before I tell you what the order would be, see if you can predict what it would be. So in this case, it actually turns out that the order looks something like this. The slowest growing functions will be logarithmic, which makes sense. As x goes to infinity, we know logarithmic functions kind of level off, kind of grow slowly. Polynomials will be the next slowest. You can think about things that are linear or square roots. They would also be the quadratics, the cubics. So those are growing a little bit faster, but not quite as fast as exponentials. And last but not least, the one that's kind of surprising is you can treat factorial as a function, and that would actually be the fastest growing out of all of them. The reason why is because you're not just multiplying the base number by itself, you're multiplying it by all the numbers before it. So as soon as you get up to like a million factorial, now you're not just saying, that base number times itself this many times. It's that base number times all of the integers and nice numbers before it. So this would be something I would write down that I think is also kind of helpful. As x goes to infinity, logarithmic, then polynomial, then exponential, and then the head honcho is going to be the factorial. So that's going to be another reason why we mention it, because it shows up in conversation, and if we know that it grows the fastest, it can help us answer questions kind of quickly. So the next thing we have is pattern recognition for sequences. Most of you guys are really good when we did the warm-up the other day at recognizing some patterns that you see. And from those patterns, we would like to write the nth term of a sequence. What it means by an nth term of a sequence is, can I write some generic rule that will help me determine any term of the sequence that I want if I know what n is? So can I write a rule for my sequence? So it kind of goes in reverse what we did on Monday. On Monday, we were given a rule. We wrote the sequence. This is giving us the sequence. Can we write the rule? So one thing that I found that was kind of helpful immediately when I started doing something like this is it says, let's find a sequence a sub n for this one that they gave us. It's going to sound like a simplistic thing, but just write the values of n underneath the terms. So this first one would be n equals 1. The next one would be n equals 2. This one would be n equals 3. This one would be n equals 4. And I think just having that sometimes helps determine what these rules should be. So if you look at the top there, you'll see these numbers are kind of familiar to you. There's 2, 4, 8, 16, 32. See if you can write the rule without me. So if you want, pause the video and see if you can write the rule before I do. Otherwise, if you just want to talk about the rule with me, then I'd be happy to do it as well. So notice that these are just powers of 2, right? So that's 2 to the first. This is 2 squared. 2 to the third for 8, 2 to the fourth. So in this case, I would say the numerator just looks like powers of 2. So let's say that it's 2, but instead of saying 2 to the x, we know that x is behaving like the n variable. That would be 2 to the n. So that way, if I plug in these n equal 1, then you get 2 to the first 2, right? Then you get 2 squared, that's 4. 2 to the third, 8. 2 to the fourth, 16, and so on. So that's why it's kind of simplistic, but just writing these numbers underneath there sometimes helps you discover what's going on. Now, most people, if they were looking at the denominator, would just say that it's going up by 2. And you're not wrong. But we need a way to write this, right? So we need a way to write it kind of as a generic rule. So I noticed that for the first one, I've got 1. So I need to do something with 1 to get to 1. So now maybe not necessarily obvious. But then I also see for n equals 2 that it's 3. So I'm thinking, okay, it looks like it's just going to be 1 less than 2 times the n value, right? So for the first one, if I do 2 times 1, that's 2 minus 1 is 1. How about 3? Well, that's 2 times 2 minus 1. How about 5? Well, that's 2 times 3 minus 1. So instead of just using the number, just replace it for n. So what if I did 2 times n, and then I did minus 1? So this is kind of the way that I think about it. Start with the numbers, see if you can build the pattern, and then once you have the pattern, see if you can discover what's going on. So this would always be 1 less than 2 times the position that you're in. Now once we have this sequence, it wants us to say, is this thing going to be converging or is it going to be diverging? So for that, we can apply a limit. We can say the limit, and then say as n goes to infinity, we have 2 to the n over 2n minus 1. Now if we plug in infinity, you'll notice that we'll get something really big positive on top and really big positive on the bottom. And if you want, you can take a derivative with L'Hopital's and apply what you know. We know the derivative for something like 2 to the n would be the natural log of 2 times 2 to the n. The derivative for 2n minus 1 would just be 2. So then if you reapply your limits, you'll get infinity over 1, which diverges. But you can also talk about this in terms of functions, right? So tell me, what kind of function do we have up top, this 2 to the n? Well, that's exponential, right? How about on the bottom? We have linear. So think about it. What's going to grow faster over time, exponentials or linear? Well, exponentials are going to defeat linear functions in a first round knockout all the time. So this actually would be a limit that does not exist, right? It goes to positive infinity, which means the limit value itself or the sequence is going to diverge. All right. So these are the tricky ones. I know a lot of students in years past have said the part of having to write the rule is the part that's a little bit tricky. So if you want, maybe as a challenge to you, how about example 6? Without me telling you the answer, maybe I'll tell people the answer in class the next time that we meet. Could you try to write a rule for something like this? So give it a go, see what happens. If I could give you a hint, for the numerator, maybe you're not as familiar with things like 2, 8, 26, 80, and 242 in succession, but what numbers are they really close to? They are really close. All those numerators are really close to something that you're actually quite familiar with, and I think that will help out. And then for the denominator, it's not a pattern that we've seen a lot, but we're starting to see a lot more of it recently. So see if you can write a rule, right? In this case, maybe we'll call it b sub n. And then if you write a rule for b sub n, then after you write that rule and you check it to make sure that it works, let the limit as n goes to infinity and then check it for b sub n and see does it converge or diverge. And I'll share that with you in our next class session. So then for day 2, we'd start with these little starters. We'll say, well, what's the infinite limit of these sequences that are in front of you? So if you want, you can pause the video. Otherwise, we'll just jump in. We can say the limit as n goes to infinity. How about for 5n squared over n squared plus 2? So in this case, we notice we have the degrees are the same, right? We have an n squared on top and an n squared on the bottom. So then if we apply the elephant rules, if we have the same exponents in numerator and denominator, then we can divide the coefficients. So in this case, it would just be 5. How about the limit as n goes to infinity of 5 minus 1 over n squared? Well, we know the limit as n approaches any number of a constant is still going to be constant. But where we can apply the infinite limit is on the second part. 1 over an insanely large positive number would just get closer and closer to 0. So this would be 5 minus 0, or would be just 5. Now at this point, students usually do something kind of funny. They see a couple answers start to be 5, so then they assume that the next answers are always going to be 5. So let's see if that's true. So if you wanted to write them, we have these. So how about this one? We have the limit as n goes to infinity of 5n over the square root of n squared plus 4. Now this one's kind of tricky, but here's the way that I would think about it. Now the top is going to go to infinity, right? If you plug in a large positive value. But let's talk about this square root of n squared plus 4. As n goes to infinity, then squaring it is going to have a huge impact on that large positive number because it's going to get even more crazy large positive. But adding 4 is not going to impact it as much as n is increasing like crazy, right? The squaring is going to change things, but adding 4 to a number that's already insanely large positive is actually not going to have a huge impact on it. So for that reason, in a question like this, you could actually say that this plus 4 is negligible. The square root of n would, or square root of n squared would just turn into n. So really, this question would be just the limit as n goes to infinity of 5n over n. So since they have the same degree, you can divide the coefficients, and wouldn't you know it, the answer here also comes back as 5. Now how about this last one? Here I have the limit as n goes to infinity of 1 plus negative 1 to the n. But then what I notice is if I take negative 1 to a large positive power, then that's going to alternate, won't it? So if I pick an even power, it would give you 1 plus negative 1 to an even would be 1 plus 1, or 2. But then if I have an odd exponent, then 1 plus negative 1 to an odd would be 1 plus negative 1, which would be 0. So I think this would just go between 0 and 2, 0 and 2, 0 and 2. Would it be getting closer to a specific number? No. So in this case, you could say the limit does not exist, right? It's oscillating between these two values. So for that reason, you would say this sequence diverges. All right, so let's dive into the new conversation, which was this idea of something being monotonic versus non-monotonic. So this sounds kind of sophisticated, but is really not so bad. So we know that monotonic means that the terms of a sequence are either non-decreasing or non-increasing. So in the case that you have something non-decreasing, then you're saying that every next term in line is either greater than or equal to the term before it. So notice it's not saying that it's increasing, right? Non-decreasing, the way that it's worded, implies that it could stay the same. And vice versa. If terms are non-increasing, then you can say as the terms go on from next term to next term, then they're going down. They can be either less than or equal to the term before it. So in this case, something is monotonic or monotone if it doesn't change, or it's trending in the same direction. So again, non-decreasing means either stays the same or is increasing. Non-increasing is either staying the same or decreasing. So as you see, it allows for it to stay the same, which is not true for just the words like decreasing and strictly increasing. The second big word for today would be boundedness. If a function is bounded or a sequence is bounded, then we know that it's going to have an upper or a lower limit. So we say a sequence is bounded above if there's some number that the sequence never goes above. We say a sequence is bounded below if there is a number that it never goes below. But it is also possible that the sequence is bounded on top and the bottom. In that case, we would just say that it's bounded. If you just say that a sequence is bounded by itself, then you're implying that it has a top bound and it has a lower bound. But if it just has one, let's say it's bounded below and not bounded above, then you have to specify bounded below and vice versa for bounded above. But if you just say the word bounded, then it is implied that you're saying both top and bottom. So how about a picture of what this would look like, right? How about this one on the left? Would the blue or the pink function be bounded? Well, the blue one, definitely not, right? It looks like it goes up and down from positive to negative infinity. And then for the pink one, it does actually look like it's going to be bounded. We have those two kind of horizontal asymptotes. It looks like it would be bounded below by this horizontal, and it looks like it would be bounded above by this one. How about all those trig functions that you guys saw in pre-calculus? Things like cosine or sine. Would they be bounded? In this case, yes, right? You could say bounded because they're bounded above and below. But if I saw one that was bounded below but not above, then I have to specify that. So bounded just means that they don't go above or don't go below a certain value. So how could you determine whether a sequence is monotonic, right? I want to know, is it non-decreasing? Is it non-increasing? You could just list off a couple terms. So let's say that I was doing letter A. I was doing A sub n. So I can start with n equals 1. If I plug in n equals 1, I get 3 plus negative 1 to the first, which is 2. How about if I plug in 2? Then I get 3 plus negative 1 squared, which is 3 plus 1, which is 4. Then how about n equals 3? This would be 3 plus negative 1 to the third, which is 2. You see it would just be bouncing back and forth. But notice that it's never going to go lower than 2. It's never going to go higher than 4. So for this reason, you would say that this one is bounded. It's bounded above by 4. It's bounded below by 2. How about letter B? So this is B sub n. If I take n equals 1 and I plug it in, I'll get 2 over 1 plus 1, which is also 2. How about if I plug in 2? I get 4 on the top there. 1 plus 2 is 3, something like this. How about n equals 3? So if I plug in 3, I'll get 6 in the numerator. 1 plus 3 is 4, so something like this. How about n equals 4? So we did mention that the first one was bounded, but we should have said if it's also monotonic. I forgot to mention that. So in this case, if you're looking at it, we go 2, 4, 2, 4. You see that it's not just non-decreasing or non-increasing. It looks like it increases from 2 to 4 and then decreases from 4 to 2. So this one would be not monotonic, right? It's not staying the same or increasing, decreasing. In this case, it increased and then decreased. So in this case, it would be not monotonic. Sorry. So then for this one, how about n equals 4? If I take 4 and plug it in, then the numerator I believe would be 8. The denominator would be 1 plus 4, which is 5. And it looks like if you go over these decimals, we have 1, we have 1.3 repeating, 1.5. It looks like it's either increasing or staying the same. So I would say that's non-decreasing. I would say this one, definitely monotonic. Since we have the idea of bounded kind of right in front of us, I would say, is it bounded above or bounded below? Well, it looks like it is increasing, but is there any value that it would never be lower than? I don't think it would ever be lower than 1, right? If it starts at 1 and it's increasing, then I could say that it's bounded. In this case, bounded below, right? It's never going to get lower than 1, but it does look like it's going to increase if you keep going with the terms. So how about letter C? So for this one, we have C sub n. Let's say we plug in 1. 1 squared is 1. So then if we plug in 1 to the denominator, 2 times 1 minus 1 is just 1. How about n equals 2? This would be 4 over 2 squared minus 1, which is 3. How about n equals 3? So then you'd have 3 squared, so this is 9, over 2 to the third, which is 8, minus 1, which is 7. How about n equals 4? Well, if you plug in 4, I think you'll have 16 over 2 to the fourth, which is 16 minus 1, which is 15. So then if you check these decimals, you actually see it starts at 1, then it goes to 1.3 repeating, then maybe it starts to get larger, but then actually it starts to decrease here. So it's increasing and then starts to decrease. So for that reason, it would not be monotonic. But you could talk about it being bounded because it looks like it's not going to go below 1 for what I can see, but you probably would want to do a couple more terms in order to determine if it's actually bounded or not. Because what if you get down to the 5th, 6th, 7th, 10th term and it gets lower than 1? Then all of a sudden, if you said that 1 was a lower bound, then maybe it's not. But in our case, we can say it's not monotonic because it increases and then it decreases. So to help you visualize what's going on, here are a couple pictures, right? So we can see what we talked about with letter A. We can see that it's bounded above and bounded below. But we'll say that it's definitely not monotonic, right? Because it increases and then decreases. How about in letter B? We said that it was monotonically increasing, which means that it's non-decreasing. And we did say that there was like a lower bound, so maybe bounded below by 1, because if it's monotonically increasing, it doesn't look like it's going to get lower than 1. How about for letter C? So for what we saw, we said it was not monotonic, right? Because it was increasing and then decreasing. You could maybe say from what we can see in this picture, at least to the 4th term, that it might be bounded above, it might be bounded below. But this one's going to be kind of sneaky, because what if we keep doing it, and then what if we get to like the 5th term, the 6th term? It could get lower than 1. It could get more than C sub 2. So for our purposes, maybe we'll say C is not monotonic, but if you want to know if it's bounded, then maybe list off some more terms. Now the last thing that it talks about to consider is kind of an important theorem. So it says if a sequence is bounded and monotonic, then it has to converge. And it actually makes a lot of sense as to why this is true. If it's bounded, that means that it's not going to go higher or lower than a specific value. If it's monotonic, then it's either non-decreasing or non-increasing. That means that over time, it's either got to get closer to its upper bound or get closer to its lower bound. So if that's the case, that something is getting infinitely close to an upper bound or a lower bound over time, then it has to converge to that upper bound or that lower bound. So for that reason, kind of a big theorem for us. If a sequence is bounded and monotonic, that means it has to converge for sure. So the last example that we have is these sequences here. It talks about both bounded and monotonic. So it says the sequence A sub n, 1 over n, is bounded and monotonic, so it has to converge. So if you think about it for letter A, let's say you have 1 over n, just kind of going term by term. If I plug in 1, I get 1 over 1, then I get 1 over 2, then I get 1 over 3, and so on. So in this case, you could say it looks like it's monotonically decreasing, right? This number is getting smaller, 1, a half, a third, a fourth. It looks like it's getting smaller. And it's going to be bounded below, right? In this case, bounded below by 0. We're going to get like 1 over a million, but that's really close to 0, but never going to get to 0 or past it. So because it's bounded and monotonic, this would have to converge. You could do something very similar for B. You can plug in some values. You'll see that it's monotonic, but it's not bounded in terms of bounded both on the top and the bottom. It would be bounded below, but not on top. So for that reason, you couldn't say anything about it converging because it doesn't meet the criteria. It's got to be bounded and monotonic. And the last one, the divergent sequence is bounded but not monotonic. So C is kind of a quick one. You could say that if I was running with the values, right? If I pick 1, then I would get -1. If I pick 2, then I get +1. So I know that it's just going to oscillate between these two things. So what you can say is that it's bounded, right? The highest it goes is 1. The lowest it goes is -1. But it's not monotonic because it's not non-decreasing or non-increasing, right? The first thing it does is increase, but then it decreases. So for that reason, it's not monotonic, and we can't say anything about its convergence. So if you want, as an extra little practice, you could try to find the nth term of these. Could you write a rule for these things that I have here? And I would say that's going to lead us into the conversation for next week. All right, guys. Thanks for watching the video. I hope you have a great rest of your day. Reach out to me if you need anything. I'd be happy to help explain. See you next time. Bye.